Hi everyone, I'm Shady Atia, professor at Liège University in Belgium, and today we are going to attend the Building Simulation Conference 2026 in Hong Kong. I am just arrived at the Hong Kong University of Science and Technology campus, as you can see, and we are heading to the registration. So the overall theme of the Building Simulation Conference this year is climate neutrality in buildings and cities, but the focus that I will share with you is mainly artificial intelligence applications in the built environment and for building simulation in general. There will be many papers, many sessions we will attend and join together. There will be a paper about automation of EnergyPlus, large language models, automation, infrared, radar data for real building processing, all the graph neural network working on optimization, urban scale energy predictions, and different energy flexibility models and management, grid interaction. Also, I will focus on physics-informed neutral network, replacing expertise, CFDs, HVAC, grid controls, all over model predictive controls, generative models also, and probabilistic energy forecasting. I will focus also on a second part of the conference, which is very important, the computation or the computing. So the computing question will be underneath all these topics, and I will focus on the GPU, the CPU, the cloud versus the edge, and what kind of data centers are implicated in this practice. So data center will be a key topic of this conference, and I will focus on a special session that will be on day 3, because data centers, they need to be carbon neutral, and they will require a lot of renewable energy to be generated on site while addressing the cooling and addressing different problems of flexibility and load match overall. So all these topics I will cover during these 3 days. Stay tuned and let's enjoy the conference. Hi, we are just a couple of minutes ahead of the opening ceremony of the Building Simulation 2026 in Hong Kong at Hong Kong University or Hong Kong Science and Technology. We will have in this morning 2 important lectures, one by Professor Chen Qingyan about LLM for building energy and environment design and operation. Then we will have a second one at 11:25 about intelligent computing in the age of artificial intelligence by Professor Peter de Wilder from Lund University. Last lecture on the morning will be also Professor Yan Da from Tsinghua University, Beijing. The title will be Integrating AI with Domain Knowledge for Building Energy System. So let's follow those 3 important lectures and let's stay tuned about the keynotes of the morning.
Actually, a lot of people already use a different type of AI technology to do this. And here, just to give you a few examples how people did that. You know, in the early days, you know, genetic algorithm is a very important issue, so you can use that to do the shape optimization. And then there's a lot of other development. I just show some of those here. However, those type of design before the large language model is still based on certain type of experience. It's very difficult. And now with the large language model, I think we can do a better job. And this is especially true after the GPT-4 was published. And I believe among the audience here, everyone uses the large language model. No matter you use it for English editing, writing poems, or writing even scientific papers published in Science and Nature, I don't know. But definitely it's a possibility, right? So if we think about to design a building, and of course, in the past, it's really the architects start with the conceptual design. And then you communicate with the user and then do a little bit of iteration And then you might find the two sides agree to each other, and that's form the preliminary design. And of course, the engineers, like most of us, will chip in at the time. You will propose certain type of energy systems, ventilation system, etc. We can do a little bit differently. We can communicate, with the large language model, and I think everyone can become a kind of architect or engineer. You don't need the professional knowledge, and then you should be able to work out something you like. Okay, so how do we do this? I mean, this is the flow we are doing, and it's starting from the scratch until the end of the energy simulation. So I believe many of us are using different type of simulation tools, whether it's EnergyPlus or the CFD or radiance for lighting, acoustic, etc. We use some type of simulation tool. In the past, the simulation tools are not that easy to use, because you just think about the EnergyPlus, how many inputs, parameters you have, right? And then you often can make a small mistakes by asking questions or feeding a few pictures, and then you can develop into a very nice one, and that's what I'm going to do. Okay, so this is our approach. We'll start with the conceptual design, preliminary design, and develop design in a very similar way, like you work with the architects and engineers together. So what I do is I'm going to take the M building at Hong Kong Polytechnic University campus, and that building is the tallest building on campus, and our president's office is on the top floor. So this building, as you can see, currently has a floor area of 16,000 square meters. The total is 18 floors. Okay, the building was built about 20 years ago. I mean, the outside looking is we entered into the GPT-4. Okay, we said that's the floor I want, and then the floor height, then the size is on the 40 meter by 37 meter, because we are located in the center of Kowloon, very small area. Okay, so this type of input, I think most of us can do it, right? Then it generated something on the top left. Of course, the list doesn't look as very interesting. So we said, okay, the current design does not look as atypically pre-generate alternative shape. So then it generates something on the upper right. It's still not interesting. We said, can you improve? Then it generates something on the bottom right. Again, not very good. And then I'm very patient, ask one more time, can you do something better? It generated the one on the lower left. It's not interesting enough, right? This is our building. And then I said, okay, large language model, GPT-4 can only do something like the one I just showed you here, and that take one flows out. Okay, and then we give the prompt. As you can see here, I prefer the staggered volumes with the sky gardens design. Please provide a preliminary design that meets the specific requirements. So this is not a specific command. Then it generates a building on the right. Okay, of course, we do a little bit further analysis by using EnergyPlus, and then we can calculate what's the energy used. Okay, this is a very simple calculation. Later I will show you a little bit more detail how we did this. So that's 273 kilowatt per square meter per year. And they also generate a wall ratio of 0.41. So that means not very close to what I originally designed, that's 0.56, okay? Then the floor area is also reducing the energy further. Okay, I mean, you can see here, the reduction from 273 to 171.1 and then 271.3. And that same is reached to the limit. Large language model, although they read almost everything in the literature, but cannot do anything further. Okay, that's the limit. And the building design is not desirable. So if I stop here, you might conclude the large language model is not good for architectural design. Then probably many people don't agree with my conclusion, right? Because I'm just one single user and did a terrible job, and then I conclude large language model is no good. So then, because of this, as I show you here, the building design is not very good. But of course, the large language model is not that bad, okay? Because this one, we can recommend you something, okay? So this is the systems they are finally recommend as soon as you challenge the large language model. Large language model, I mean the ability of a large language model to do the design really depends on how intelligent the user is. The smarter you are, the tougher question you ask, the better design it will be. Okay, so that's the result as you can see here. When we do the building design, the architectural design, we only save about 4.2% of energy. But if you ask a large language model to improve the HVAC design, which is more directly related to the energy, so as you can see on the right chart, we can save about 24.8% of energy. And that's amazing. Because normally we think the architect can change the building form a little bit, can save more energy, and engineer can do little. But the reality in using large language model, we find it's just the opposite. Okay, engineers can do more because now a lot of systems we develop can really help the building design. Okay, so that's the conclusion. We save 28%. But the building still looks bad, okay? The large language model seems can do something. So large language, this is the work done by my student Wen, who is an architect. And I say, you are trained as an architect, but you can't. And then he said, oh yeah, by using large language model, he definitely can generate something, buildings very beautiful. So this is just 3 examples generated by large language model, just by picture. Okay, you don't ask about to design something with the limitation, the number of floors, etc. But this is a nice building. Okay. Then we said, okay, let's just take one building out in the middle, and then just generate it into a building which can be used for energy simulation. Then it's not very good. Okay, so we think we have because later on we find that picture is only a picture. You see the window on the left, you see the floor, you see the walls there, but in terms for large language model, it's just a different type of color. They don't know. Large language model actually doesn't know there's a window. So we have to use this cloud 3.7 summit in order to distinguish which one is window, which one is shading, etc. So we have to, this is the cloud 3.7, okay, a little bit old version, but we still find that the ability to identify different building components is very limited. And therefore, we have to start with something different. Okay, we want, as you can see, when I have decomposed the 3D model, you see along the diagonal side, there's a window, external wall, the shading device. Now we can take it out. Because it's a 3D model, you can do a lot of things on that. And we have to, some of them, sometimes it doesn't align to each other because a lot of lines doesn't mean anything. So you have to do a little bit of editing onto that. And then you can get a geometry for building simulation. Okay, so I use my original view, that's the current picture. I should take a little picture from the campus, and then feed it into Huiyan. And then you see they start to process and then generate a 3D building. Yes, I'm almost there. Thank you. So let's 3D. And when we compare with this 3D model with the reality we have, we find not exactly the same, but very close to each other. So that's an amazing thing, because you just give a two-dimensional picture. They can generate it into a 3D model, which can be used for energy simulation. So we get this energy simulation 285.7, okay? And we also build an energy plus simulation model by hand. And our simulation result is 286.5. I mean, very close to each other. And I think that's really great, because in the past, if I ask a student, to do a simulation from the scratch, it takes a few weeks. Now with this one, it's just a few minutes, it's done. And that's why I think large language models really can help us to do a lot of things. But of course, let the buildings to generate one more image. And now with this large vision model, you can get a very beautiful 3D and model. This again is a 3D, I don't know, well, it's a 3D model. And then you generated something which can be read by EnergyPlus, and then you do the energy simulation. So you can see that we have now two different types of buildings. One is a real building, another originally generated from large language model GPT-5, and eventually we find that you can do the analysis. Not building looks nicer, but also safer energy. And this is something that's very difficult in the past, because the architect can do the building improvement, but the engineer has a difficult time, especially in the preliminary design, to work with them. Okay, so because time is limited, but I still wanted to spend a minute to explain to you, we don't stop on the building design. We also can do the building control and operation. Okay. In the past, you can only say this in this room, use a fungus 7-point scale, very hot, warm, and then neutral. We have a top expert, Richard here. Let's say the 7-point scale we use all the time. It's very difficult for me to tell the difference between very hot and hot, okay? Because everyone have a different perception. But then normally we can say something, well, I feel a little bit cold because the wind is blowing from my neck. Why don't we use this language to train the model and adjust the HVAC system? So we did that. We use Qiwen. Okay, so this one, you can identify the language and then develop the control strategy. And we allow, in this building, we allow to change the wind direction, temperature, speed, just 3 parameters. Okay, now here you can see we have a 3 different type of control. On-off control, very easy, everyone do that. PID, normal, I believe for this room, we use PID control. Large language model, they also can produce control command. You can see that the energy saving, this is the comfort, they can adjust more or less as beautiful as PID. But we save the energy, and here is the PMV. Okay, this is the comfort level. As you can see here, on-off is not very comfortable. Large language model, PID control are very compatible. That's the real control, as you can see here, temperature, relative humidity, velocity, and PMV. Okay, so I think for Richard, you probably will like it that you see almost 0 PMV. Okay, this means perfect. So that really means large language model is very great. So I think let's conclude my talk. Thank you very much.
In this talk, I want to talk about intelligent computing and what we're trying to do. We're in a building simulation conference, and we have a lot of tools at our disposal. But the question is, well, what do we really want to do in the next 10 years, right? I'm 55, so I've got a decade to go. Where am I going to take this? And that is important for things like IBIPSA, the International Building Performance Simulation, in which I'm very active. It's important for the journal that is behind the conference today, the Building Simulation Journal. And so what I want to do today is go reflect a bit on why we do this stuff and what we want to achieve with this. Then what is changing in the age of AI, and Professor Chen gave me a hard act to follow there, but I want to reflect a little bit on that. Go into opportunities and challenges, and then start thinking about how we can improve our discipline. So the first slide is really to set the scene, right? And we talked about in the beginning zero carbon cities, but there's other things that we need to do. We need to make sure that we deal with the environment, but we also deal with extreme events. We need to provide comfort. Only variety can absorb variety. The trade-off between simple and complex models, high bias, low variance, and the other way around. Vapnik's principle: do not solve a more general problem that needs to be actually solved. Do we overshoot? And what I also like is Cole's law. So all these complex systems typically are built from simpler systems that we know that work. Yeah? So don't try to make something very complex in one go, but build it from pieces that you know are already based and demonstrated to work well. So if I then look where we are and the trends where we are, I take this old picture from my old mentor, Fried Augenbroek. He published a paper in Energy and Buildings about building simulation trends in the new millennium, 2003. And in there he had this progression where you go from differential equations in the 1970s, and branching out into different domains, starting to look at interoperability with the Combined project, and he projected from there where things were going. Yeah? And you need to keep in mind that his original publication was at the first blue line. We're now at the second line. What I find interesting is that in this graph, at the turn of the century, he was talking in the future about pervasive and invisible models. And I think what we've just seen in the first keynote is really that stuff, right? So we have AI combined with building simulation, and it starts to go in the background. We're not longer actually seeing and playing with the models, it's in the background. And urban modeling, stock modeling, well, you can read the list. But what is emerging is also this area at the bottom, for artificial intelligence, large language models, machine learning, digital twins, twinning, data analysis. They're really getting more and more attention, and they're growing into the domain. But if you then actually try to do this in real practice and see what tools people are struggling with, this is quite a complex field yet. This is work from one of my new PhD students in Lund, and he's looking at this BIM to BEM challenge. And what we see here is on the left hand a couple of architectural tools, on the right hand simulation tools. Sense of building simulations, if you have not seen those stem from Strasbourg. First Professor Tom Maver and Joe Clark repeated them 25 years later. But these are things that for the development of building simulation, we say, well, these are things that risk that we need to look at. We need to make sure that we are not blinded by the technology we have in front of us. And I think we need to keep that in mind as well as we move forward. Then we've got AI in the picture, yeah, and quite attractive. All my students want to work with this, and that is great on one hand. And you observe a shift from, on the one side, the traditional building simulation, so where we develop models and tools, where we typically do a static analysis, where we look at the design stage, where we have deterministic outputs, and where experts are quite important. And when you start working with AI, then we get more models as part of a framework, to get more continuous modeling going on, more lifecycle integration, more looking at outputs with uncertainty and increased automation. And that means that this stuff goes in this invisible direction that Fried Augenbroek had. It might be worth at this point to just briefly remind us of AI. Yes? So AI is typically a computer system that does tasks that thus far have been done by humans. So learning, reasoning, designing. And in the background there is weak AI and strong AI, if you have not heard about that, so a system that performs specific tasks, and the debate about the more artificial general intelligence. If you look at the close-up stick, at the moment a lot of effort is going into the agent-based systems, and that actually become small models that do specific tasks and are connected into a larger whole. Yeah? Keep in mind, if you talk about AI, that's typically a suitcase term, as I label it. So if you look at artificial intelligence and you start studying all the aspects in there, you open the suitcase, you find more little bags that you need to open, and each one is another area, so you can explore it quite in depth. But it's not just machine learning, it is also natural language processing, it is computer vision, it is creativity, all that stuff sits in there. Yeah? But a lot of the work that we see is also in machine learning, and that is the statistical algorithms that learn from data without human intervention, and that's quite promising and doing a lot of the stuff that we see. And the graph there kind of shows some of the subfields and how that develops at the moment. Also, maybe worth to very briefly remind us here that AI sometimes feels what used to be weeks of work now can be done in minutes. Integration across the life cycle, the multiple performance things, combining that. Hopefully deeper insights, causality, I've got a slide on that later on. And what it should all be about always is better decision support. Are we getting there? Well, my answer is not so sure. Yeah, I do a lot of reviewing in my role as associate editor for Advanced Engineering Informatics. This is a typical paper I get. There's a lot of claims, yeah, and they always start with a high level. There's a big problem, like my slide about what is burning in the world that needs to be helped along. And then we say, okay, we're going to do something, and typically they drill down in some algorithm, and they show a marginal improvement, and they claim that that's a new paradigm. I think we should look back at things and say, okay, overall, where are we going with this discipline? What is happening to building simulation and built environment, and what can we actually achieve there? And that also brings some of the AI concerns into focus. Yeah? So, can we interpret the models, and actually can we trust what the model gives us? And so it was great to see validation in the first keynote, but a lot of that is very hard to do, especially if you're at the design stage. How valid is it? And we know all those models, machine learning models, you train them on a certain domain, and the risk is always if you extrapolate beyond that domain, that's where the hallucinations start. Yeah, so you need to be careful about that. You need to be very careful about the data you put in there, whether there's any unexpected data, assumptions in there, bias, very, very tricky field. Are the systems actually stable? Can we extrapolate? Are we actually putting too much trust in the model to automatically make decisions for us? As a human being, do we just absolve everything to the AI, or are we in control? Is there misalignment, overconfidence? And another question, if models get older, who is in charge of keeping them up to date? Can we maintain them? Can they drift? Are they fragmenting? So we need to look at those things. Where I think all this stuff really is interesting is the causal models. I want to bring that in. And this is my good friend Chilson Park from Seoul National University. He does separate keynotes and has been here doing that talk at Tsinghua University recently, and he also gave that presentation in Lund. He's talking about causality in models, and where we go here. These parsimonious models are really interesting. It's really the talk about the left-hand side, some examples, how you do that. So whether you split and have too many variables in there, or whether you kind of make it simple, and because it's simple, you can easily predict what happens. On the right-hand graph, there's straight away a footnote to that assumption. Yeah? So on the one hand, it seems like the way that is forward, but I found one paper that questions this. So Occam's razor about always taking the simplest model. That is what we see in the statistical modeling world. The world of overfitting. There's this assumption that when you go from a model and you remove the bias in there and you start training on the noise on the system, you've got the overfitting in there. This paper at the bottom actually claims that for some areas where you have real control, actually you could model the noise and then you would jump beyond that thing and come in the path where actually actually you are able to do stuff. But it's a question, and I think we are really, with our models, we're very much trapped in the first trough, and we need to escape from that if we want to have those very high detailed models make any sense for us. So take home points from my keynote. Really, it's not about better models in itself, but it's about better decisions and about link them to the built environment. More data, more computation is not necessarily the solution. Yeah? I think we need to look more at causal understanding and maybe for the moment fitness for purpose and parsimony, and actually whether we use the simpler models for what we need to do. And for AI, really fascinating technology, but we need to use it responsibly because otherwise our clients will not accept that and will come back to us and go buy it. So with that, I think I'm hopefully on time.
AI is extremely important area in the simulation area. And also in the building and system management, we need to quite a lot of dealing with the flexibility of building and also demand response. The integration of renewable energy and also a change the building from the consumer to prosumer. This means you produce energy as well as use energy. So the building energy system controls became much more complex than before. They bring a lot of thermal iterate and also uncertainty and also variation of system working conditions. So this gives us quite a lot of challenge. So we're using a lot of prediction-based control and into the building energy systems. The next 24 hours of prediction always useful to predict the weather and operation data, how this will influence on the systems. So the intensive studies of AI has been induced to the enhanced performance of prediction-based control. As we know that AI is facing a lot of bottlenecks. There's a lot of good things we have taught, but there's a lot of shortcomings. We're meeting a lot of bottlenecks, including the physical consistency and also generalizability and also robustness in the application of building energy system control. So if we're meeting this kind of challenge, how we can bridge the gap between the AI models. We pick AI model into application, but they still have 1 mile far from the real engineering applications. We need to fill in the gap. So today I will present 2 parts of the initial research from my side. First one is a very interesting topic. It's dealing with how this happened. We always using a lot of forecasting model, but sometimes we say that we're using the forecasting model, the same model implement in the 2 cases. In the one case, it perform very good. Another case, it perform very bad. And what is the basic phenomenon come from? Sometimes we forecast a load profile in a low regularity. That means it's a rhythm profile. Another one is very regular, like we have a big shopping mall. The cooling pattern is very regular. So if we use the same model, even the same accuracy of the same model level of detail, and in the low regularity scenarios, they get very bad result. But in a high regularity scenarios, they get very good, very low errors in the forecasting. So how we can evaluate one kind of phenomena or time series itself is it's easy to predict or very hard to predict. That's the question. So we would like to estimate this kind of predictability. That means it's easy to predict or not easy to predict by the different resolution. One is from the temporal resolution, one is from spatial resolution. Another one is numerical resolution, 3 pass. Here we induce one kind of we say information entropy index. It's MIC. It's different from the VPAN's MIC. It's maximum mutual information. It's different, but it's the same function. And the MIC is the correlation evaluation index. And this is used to identify the linear or nonlinear correlation between the two variables, x and y. And we're using this to measure the MIC, measure the predictability by the current time series. So you can see that when the higher noise means it's hard to predict, they will get very low MIC value. So here we induce a lot of data by the help of Agent Chong from NUS. We collect occupancy data in an academic building, and with 5 floors. We counting how many people are there in one building in different floors, and we collect around 1 year data, and the interval is 5 minutes. And by this kind of data, we say we can compare the predictivity with the ability with the progress indicator PIE together with MIC, the new indicator. We find that the new proposed MIC data is MIC matrix is very good to present the predictivity. It's dispute very long period, and also multiplicity is better, much better than PIC. And if we see from the phenomena part, if we say we would like to predict the 5 minutes interval, people's occupant numbers in one building is very hard. And if we would predict a day, accumulate the occupant numbers in a day, that will be much easier. So by this kind of MIC indicator, we can say when the time we say spatial resolution go detailed, the predictivity will be lower, much lower by MIC. And if we look at the spatial resolution, that means if we want to estimate one floor, one room, people's number, it's sometimes tricky, much tricky. And if we would like to estimate the whole building or whole city people, that will be much easy to forecast. So by the MIC, we can say that when the final spatial resolution it is, the lower predictability it will be. And if we look at how we confirm the numerical resolution part, that means if we're counting one person by one person, it's really hard. But if we would like to count every 1,000 people, that will be much easier. By this kind of data, we can say the MIC works much better than before. And another very important and very interesting phenomenon we found that if we look at one kind of the time series, is the MIC is too low or too high. That will all the models, accurate model, high model or complex model or simplified model, they perform almost the same. But in the middle part, MIC values in the middle part, the better or with the complex model will work much better. That's more like with the LOD of the model. If we look at the very accurate, very hard to predict data, then we need to use a very complex model to do that. So that is very interesting. I think very interesting pioneer work we can do. We would like to use the MIC to predict the time series predictivity of a matrix, and using this kind of matrix, we can easily to identify how the time series data is easy to predict or not. This is one kind of work we have done. Another one is we would like to do some control-oriented load prediction matrix. Normally, like we're using the prediction-based control. Firstly, we identify the 24 hours prediction of the cooling load. then we can using it for the final control optimization to determine the control and make the final to get the final cost of the your chiller and also the time, summer time. And we definitely think the accurate model will perform better. That means if you use very accurate predictive model, you definitely can save much money compared with the rough model. And we compared all the data, each dot is one predictive model. This is very interesting that in principle, the better prediction, the lower error, they will definitely have a better control performance. But not very rarely, that is the highest cost reduction point is not the most accurate model. The most accurate model is not perform the best. That is sometimes is a little bit different than our estimation. Why this happen? It's just because if we look at the ice storage systems, in the there will be if we look at the arrow, we're using statistical arrow like CVMC or something. It's you look at all the 24 hours arrow as equal. You just say every time arrow is equal, and we do the statistical counting for all the things together. But in the application, for instance, like the critical hour, like the peak price, electrical price hour, will be much more sensitive to the final performance. And also this kind of thing is not only by the price, but also by the seasons. If you look at the transition seasons, the total load is very low. Then we can storage enough time, enough ice in time during the winter time. In the night time, then we can release the ice during the daytime. So whatever the error is, it will be worse. So this is make our system more complex. So we propose one dynamic weighting factor arrow to pick out, the best prediction model for the thermal storage system. And here we consider the two parts. One part is the system relevant weighting. It reflects the influence of the TOU trough. And also another one is temporal relative weight. It's including the influence of the temporal order of the control structure. And by this kind of new we say DWE arrow, that is another kind of arrow, is compared with probably the CVRMSE. We may think that the DWE here is performance better, is picked the best forecasting model, and the energy reduction, cost reduction is the best. And we put all these things to the different kind of quite a lot of buildings. We can see that the compactness and also molten honesty. That means the chains will be much better than the other numerical, statistical based arrows. And it's very interesting that from the rule-based control, when you implement AI into it, it significantly improves our performance. But still, if we input our domain knowledge, our physical knowledge, it will still have around 2% of the improvement. That's something I would like to say today. That means we have a lot of knowledge for domain knowledge, how we can implement this into the final application. So this DWE can be applied, you can got the tool based on the website, and also this kind of DWE can be easily implemented into the thermal storage, battery systems, all this kind of prediction-based control. But the problem is we do the building simulation quite a long time. We previously using a lot of physical based of a model to improve our design and planning. And now we got a lot of data. We find that the data-driven model is much more easy to use and very accurate. And now is sometimes we can meet in some middle point. That's we're using some part of the data-driven and some part of the physical-driven. So how we can bridge the gap between the AI model and with the application target. So this is quite a big challenge we are facing now. So here we do some initial discussion based on this. We would like to improve the performance of the AI in buildings in 4 parts. The first part is data processing. We can integrate domain knowledge and physical laws and equipment characteristic and operation constraint to transform raw data into the physical robust data from AI. You don't necessarily to put all the data into the AI model. You need to pick some valuable data into it. And also the model structure part. We can modify the model structure through inference structure choice, shaping the computational operator, and also forcing physical law by construct the transform purely AI into the physical constraint AI model. Just make our simulation or estimation more reliable. And also in the model training part, we can induce a lot of embedded domain physical laws and contrastive relationship and the temporal knowledge into hyperparameters and also loose functions. And as the final part, we can have a more performance evaluation, not just using the statistical evaluation indicators. And we can design the indicators, metrics, and the criteria that can more precisely reflect application target. So as one conclusion for the my presentation today is AI is a very powerful tool we're using for all the aspects of a building area. But we still still facing a lot of challenges, like in generalization, explainability, and the physical consistency, and many other aspects. So in the future work, we would like to have some domain knowledge and the physical law implemented into the AI to improve the final performance of the AI. And this kind of work is strongly supported by Linda and Chen Zhe, and also from Dongbing, Zixinjiang, and like Zheng O'Neill, Qingzhou, and also Xiao Wang, and also Xuan Kang from different aspects. We do a lot of discussion based on as 1 year. Thank you, everybody.
So just had lunch, very nice, had a lot of networking opportunity, met Professor Wang and different professors from the Hong Kong City University. So we'll continue the conference events and proceed with the second half of first day session.
As we all know, buildings are a major source of global energy consumption and carbon emissions. To address this, BMs are core tools for evaluating energy-saving solutions. It's a multi-agent system consisting of 5 agents: simulation agent, decision agent, optimization agent, and climate agent and complex agent. It integrates LLMs, a knowledge base, and the EnergyPlus engine to achieve autonomous closed-loop optimization with climate-adaptive decisions and explainable suggestions. Let's look at the 3 core agents. The simulation agent initializes the environment. runs EnergyPlus and extracts output metrics. The design agent acts as the brain. It uses LLM reasoning to perform performance, diagnosis, and output structure modification decisions. The optimization agent then validates these decisions against physical constraints. If the checks pass, it edits the IDF file. If not, it triggers a feedback loop for dynamic correction. We also have two supporting agents and a knowledge base. The climate agent interprets weather data to provide a climate-adapted context. The context agent processes simulation results and modification records to build memory and prioritize strategies. Crucially, our knowledge base incorporates standards from HVAC to ensure all modifications are physically valid and engineering sound. To improve efficiency, a dual early stopping mechanism was introduced. The convergence-based mode stops when improvements become negligible, where the energy-saving target mode terminates once the target is reached, enabling adaptive optimization control. So, to validate an agent, we conducted multi-dimensional experiments. This included a multi-city analysis across 7 different climate zone cities, and a multi-complexity analysis based on a robust IDF complexity scoring method, and a multi-case study covering 18 real-world building types.
Why use a multi-agent? Why not use a strong agent and from instead of a multi-agent?
We propose a total agent, an agent-based diagnostic framework that couples large language models with 3 complementary modules. So let me explain the first module in more detail. The topology-aware semantic mapping operates into 2 stages, and the stage 1 is temporal aggregation. We process continuous time series data within a diagnostic window of typically 15 minutes, extracting steady state features including average values, operating ranges, and channel directions. So we propose a total agent, an agent-based diagnostic framework that couples large language models with 3 complementary modules. So let me explain the first module in more detail. The topology-aware semantic mapping operates into 2 stages, and the stage 1 is temporal aggregation. We process continuous time series data within a diagnostic window of typically 15 minutes, extracting steady state features including average values, operating ranges, and channel directions. And we evaluate our framework using real operation data from a large international airport terminal. And the evaluation covers the cooling season from July to September 2024. And the HVAC infrastructure includes 6 chillers, 12 constant speed chilled water pumps, 8 variable frequency condenser water pumps, and 8 cooling towers, and over 100 air handling units distributed across multiple branches. So to conclude, the total agent achieves highest average diagnostic score with topology mapping contributing the most significant improvement, followed by RAG knowledge and React reasoning. The key insight is that physical topology awareness is the dominant factor to accurate HVAC diagnostics. Future work will focus on multi-building validation, real-time deployment, and extension to predictive maintenance.
So for the background, rising renewable energy penetration increases the need for demand response, and public building clusters are promising demand response resources due to their high electricity consumption, strong thermal inertial, and occupant thermal adaptability. Traditional building demand response optimization requires experts to repeatedly build mathematical models for different buildings, different energy systems, and different operational constraints. Because building systems are heterogeneous, this expert-driven process is time-consuming and difficult to scale. Recent advances in large language models provide a possible solution with strong natural language understanding, reasoning, and coding capabilities. Large language model is suitable for translating building scenario descriptions into optimization formulations and executable solver code. Existing approaches can be divided into two categories. The first is fine-tuning based method. It maps domain descriptions directly to solver code. However, this method depends heavily on high-quality training data. The second is multi-agent based method. It decomposes modeling tasks into several modular subtasks. For building demand response optimization, we believe this method is more suitable than pure fine-tuning. However, building demand response optimization modeling has several challenges. First, it has strong physical constraints. Building demand response optimization must satisfy thermophysical constraints and coupled energy balance relationships. Second, natural language descriptions are often semantically ambiguous. Different user expressions may refer to the same physical action. Third, the code implementation is very sensitive. A small error in unit conversion or constraint may produce runnable code with incorrect optimization logic. Therefore, the framework needs to inject physical knowledge, convert natural language to deterministic formulations, and regulate code implementation. To address these challenges, we propose a large language model assisted optimization model automatic generation framework. As can be seen from the left figure, the input is a natural language demand response scenario description. The core of the framework consists of two parts, a scheduling layer and an agents layer. The final output includes executable solver code, objective values, and so on. Now I will introduce the three major agents. The first one is the physical model agent. This agent includes an agent markdown file and multiple reference physical models. The agent markdown file defines when the agent should be invoked, what inputs are required, how to select models, and what actions are forbidden. The reference directory stores reusable device-level model libraries. Okay, the second one is the formulation agent. This agent translates natural language building descriptions into a structured optimization formulation. We use a 5-element formulation outputs. They are sets, parameters, decision variables, objective, and constraints. The third one is the coding agent. The coding agent converts the formulation output into runnable code. By executing code, the optimized scheduling results can be obtained. There are two key design principles. First, we use a template-based implementation. Second, the coding agent is not allowed to introduce new modeling assumptions.
So our building control task actually is a long-term control program, and during the whole life cycle of the building, the boundary condition will keep change, and even the thermal property of a building envelope may change, like building retrofit. And an agent turned at the initial stage may have more lower performance over time. So most of the current methods actually don't have the self-adaptation ability. For example, role-based control is predefined at the initial stage, and model predictive control. Although there are some methods that can update the predictive model itself, the model training at the initial stage also have to take a lot of time. And deep reinforcement learning may have a lot of data to train the model, and transfer learning and online training are also relatively difficult. So in this study, we want to develop an agent that have adaptive ability. So normally an agent can be viewed as three parts. The LM part can give the ability to the LM part have the general word knowledge, and the tools can give the ability to have interact with our reality, and the memory part can give our the potential of adaptation and evolution. So if the agent have the memory, so the agent will take actions based on the past information. And but here's one problem here, because our control task will our control task is a long-term control task, and our building will run like many years, over 10 years. So in this running process, we will collect tons of data. So how to organize the memory and which memory are useful is still both of these questions are still unclear. So in this study, we evaluate two types of memories and one mechanisms. The state memory means the the previous several steps of information, and the experiment memory represents the information, the memory that's summarized based on the event. And the gate mechanism means we will use some gate to filter out the inconsistent memory or the irrelevant information. And our experiment based on the book test platform, and we select a 5-zone test case, multi-zone office building.
So the most important insight from the first session of day one in the afternoon was that there is a shift from AI models to AI systems. The discussion moved beyond prediction towards accuracy, towards temporal reasoning across hours, days, and years. So this was a very important point. Some studies are only focusing on a day prediction or a day analysis, and some are looking at the whole year, which is more complex and more difficult and more realistic in this sense. Also, there was agent-based architecture with memory and live weather data integration and live energy consumption or comfort indicators in real time, all that coupled with different representations of occupancy, whether stochastic or deterministic. Equally important was the recognition of empirical validation and physics-informed hybrid approaches, and those remain still essential because we cannot just rely on AI, otherwise we will have confabulation, we will have completely unrealistic and uncalibrated, verified or validated models. With AI, there is an increasing combination of physics approaches, and this will be the basis for the future. The immersion vision is not smarter model, but a network of specialized AI agents. The Wendy presentation talked about AI agents that will be used to be capable to understand, predict, and combining building performance across multiple time scales, and remaining in the same time grounded in physical realities with different tasks, or maybe AI agent focusing on HVAC system, another one is focusing on the occupancy, another one is talking about focusing on the weather, another one on the envelope, and collaboratively those AI agents are running the simulation or doing deep analysis in the same time and providing feedback to inform the decision making in real time. So this is the summary of the first session of the afternoon of day 1, and stay tuned to follow up the next presentation.
So to solve this gap, we propose this open-based urban UB. Start from the data collection, then we use that data to construct the IDF files. Then we would like to use the code to modify the files. So based on that, we want to use the OpenClaw, connect that with the large language model, then define several agents, create skills for them for simulation, calibration, as well as building the compensation. Then we could use natural language to communicate with these agents and ask them to modify the codes and as well as files. So with this method, we could connect the live weather data and use API for simulation, and we could use interface to communicate with this workflow, such as Slack for our group. To be more specific, we use Nimbus to incorporate the live EKW files into the data collection. Then we use Forge to conduct the energy simulation. Use radar to compare the result with the ground truth data. After that, we could use Lens to propose the hypothesis to modify these IDF files. Then we use Chisel to modify these files, use Ledger to report the simulation result, and use Signal to send these results into Slack and to collaborate with other team members. Then we use Campus to conduct this carbonization process. This process could use Oracle to answer questions and the requirements from humans. These 9 agents are organized by this orchestral agent and to conduct the whole workflow.
This is a very simple, a very small user case that changing the window to more ratios and how many steps are involving here. Scores of several front of the layer Chinese models. We keep comparing the Kimi, DeepSeek, GNN, Minimax, and the baseline is JAMA localization model. So this is a 4B model which run on our local server.
And to summarize this second session of the first day of the afternoon, you can see that there's more recent AI models that has been compared, like Gemini, DeepSeek, Gemma, OpenClaw are all very interesting models. Most of them are Chinese. The most compelling example showed that AI-driven workflow is reducing the simulation time, sometimes from 90 minutes to 20 minutes, or even from 3 days to 1 hour. So this was also very interesting to see some presentation about that. There was also discussions about the focus on Asian memory and how agent memory get lost or agents kind of have memory loss during the process of simulation. So this will be also a very important topic in the future, and how the knowledge retention or context retention stays during the process of feeding the input and the workflow of AI-driven simulations. So the ability of AI systems to handle long engineering workflows or performance simulation workflows will be also a challenge in the future, suggesting that practical deployment will be very important, and this will be depending on how much the memory you have in your computation for the GLP and for the CPU in general, and the orchestration of the capabilities as every model in general, in order to make sure that you will have intelligence features embedded in the process itself. So this is the end of day one. See you then maybe tomorrow, then another session with the keynotes.
Before the invention of modern air conditioning, we rely actually on the energy storage to provide thermal comfort. And that used to be a industry about 100 years ago. And if you ever had the chance to
that's almost impossible in terms of labor cost or economics, really salary cost. So that's how it shows that AI can really help us. And then back to our system, how AI can help us, that's one question I tried to work in even the last 3 years. And back to our net zero target, because I want to talk a little bit how the people are here. So if you look at the world, I will not talk too much because you know the situation. But Hong Kong has a target 2050 and then 2035 with half. So it's 2050, so 10 years earlier than the mainland. Demand side and user side, and we have just building contributes 66% of carbon footprint. And because 19% electricity has been used in building. And then for the electricity, we have 75% of electricity from the supply side in Hong Kong. So it's a higher fossil fuel mix compared to the mainland. Different sectors have different types here. And we set up, for example, internally for the flexible operation, you need like 15 minutes or half hour. And for the policy, maybe you need language or event review. If you have a new policy introduced or some new technology breakthrough happen. So that's why we introduced this DES to be able to connect to technology advancement and also the policy update. Put them together, we call it the total technology linked to the simulation and with top-down policy. So that's how we introduced. And this is in fact the system we have started with the urban 3D building and started from this kind of building. Originally, we use this system to analysis of the solar potential with consideration of top, rooftop and facade and also the shape. And then this can be because city basically we have physical picture of the whole city. And then we build the system into this more like the architecture of the physical design. And firstly, we put them hierarchical, which can be put different layers and also the software layers. And then we use the hardware. For example, we have developed the building layers and the energy modules and transport modules. Those modules can be evolved over time and then put them together. And even you can put an additional feature module. For example, in other cities, we need to input module. And then there are a lot of discussion about when you cross the boundary of the center or the owner of the data, then you have the privacy issues and conflicts. That's why we use the federated design to keep the data with the owner, not transfer data rather than if, then only transfer over the boundary with either inner data or aggregate data. In such a way, we have data protection for the privacy issue from other issues. So this is the structure of our design. And we're working with different, and one of these our campus carbon neutral initiative. This is we're working with our campus. This is Bolivia campus, and we try to monitoring energy and carbon in a real time to look at each building and each different flowers, and also different department, different faculty. And when creating internal carbon trading scheme, that's where design now. We're able to do the trading between the faculty or between the department. Because the campus, like PolyU campus has roughly, as just mentioned, Hong Kong has 40 million tons of CO2 each year. And the campus is about 1,000. And Hong Kong is 1,000 of the world. So this is just 1,000 step. So we do the idea to try to develop the invitation from the campus to district, city, region. So this is the approach. And what we are doing is also physical modeling and also deep learning. And I just give one example, for example, this solar potential. And we try to do the 115 cities in real time simulation. And then we start with, for example, just one area, that's in the Shenzhen area, and in fact, it's the equivalent roughly Hong Kong island. It's the area. Firstly, it takes about 210 hours to do the real-time simulation for a whole city for the whole year. Obviously, this is not possible if you do the global scale in terms of energy consumption and in terms of cost. This is part of the work we are doing, and I found it quite interesting. I say to find rather than emphasis, the center coating can cross a different region. And based on what we have been doing for the energy building and transport, and then we try to work with those, and then we extend an additional new project, which is in fact this is a project I was asked rather than and we call the IPT for you intelligent energy and tools for structure resilience. We intend this to be more resilient. And what we are doing, in fact, is the same idea.
And we have been working with the energy building and transport, layer-based and module-based. And then we can deal with more other critical infrastructure and with other in fact the same idea, and we try to live with them. And essentially, this is some basic idea of what we are doing for this resilience for you, and it consists of major formats. One is the data hub, that's provided. We still need a lot of data to be able to connect with future data, and then use this for early warning in terms of different hazard. If you have iPhone and where is the highest practical realization. And similarly, you can do the infrastructure and different infrastructure there. And so it's can be linked to the hardware and practical infrastructure with the location and use of parts like that. This is for the based on the history data and the scenario-based or event-based prediction or the early one. And second part of digital twin, in fact, this is exactly what we have been doing for this DES system and what we can you see this picture, then is in fact we can use same platform to do other perspective. And further, if you have the everything, and then in fact immediately you can have the all different part of the application. So this is roughly what we are doing for resilience. Well, another one regarding the indicator resilience indicator, and we use the UN and World Bank framework in terms of resilience. And but one thing we try to use large language model to collect data and do the model with each other to debate. And this is roughly the idea for the using large language model to do the resilience indicator. This is our framework we have been doing right now. I cannot release the results yet because we are still doing the validation and but it has been covered 170 cities and 170 countries and 7,300 cities. In fact, without the large language model, almost impossible to collect so much data. And then there is one question of how you can trust the large language model. I believe this is always for all these kinds of study. When you use the large language model, it's easy to get data and easy to result. Yeah. That's why we're working with this part. If on the middle layers, we use 8 large language models. And then we create this corporate aggregation committee. It's like and then let them to debate to each other. And then after they discuss together, then they change the score of the resilience in terms of we have 80 different kind of indicator. In such way, we can generate updated, for example, 80 and ways for all the ranking of 7,300. I think, of course, still a lot of marks in the hand. That's why we are not really release the results, but this also here is knowledge how this can be tools can be used for our studies. And this is last slides. So what a lot of discussion. In fact, this is a question I was writing 1 year ago. I would like to really put a question to our audience. It's still my question, and I'm sure it's your question. We can use leverage the digital tools or large language model or those as the tools inside the box and to improve our efficiency of the research and development. But the next generation, I really don't know the future AI, and it's out of the box. And then it can be a lot of, course, a lot of negative discussion. That's another thing, but it's for the knowledge point of view. Large language is before current version is learning knowledge based on, in fact, based on the internet of knowledge. But when you can start to thinking and you start to interaction, and that could be great knowledge which is not the existing knowledge. And that's the one thing. I keep watching also Alpha, the DeepMind, because they have been doing with different Alpha factory. But we saw the Alpha code, how powerful can be changed the word that regards the protein, the structure, its work. And so this is more like a good catching of the how we are going to use AI and what the future of AI development. And I'm sure this is very, very interesting, isn't it, with us.
wrap up second day, there was a recording theme across sessions, which is a conversion of digital AI, digital twins, and urban systems infrastructure. Machine learning is also rapidly expanding in use and in application beyond traditional or classical building and building physics applications. This is enabling adaptive decision making in real time. And this is also a big revolution because with the digital twin, you can get the data, especially digital urban twins can reduce the carbon emissions in real time based on data while using AI to improve systems performance. Also, deep learning models coupled with physics-based simulation became also a very important immersion topic that is very promising to capture complex spatial and complex dynamics in the renewable energy system and the energy flexibility between storage, production, and energy use. Also, urban climate and real forecasting or futuristic predictive forecasting are going to be based on AI, and their accuracy and scalability and results robustness will stay an issue that is still not easily to be solved. A very important topic also that was discussed today was the ownership of data, because there is now multi-agent, multi-users, and sharing the information will be very difficult. So what's happening now in the AI world is that we find anonymization and kind of delegation of data use without transferring the ownership. So the owners, they have the data, but they just share the data after being anonymized and agglomerated, and then it is all on one platform kind of used without transferring ownership to respect privacy. So the idea of preserving privacy while enabling large-scale intelligence is becoming more and more operational and used in many cities. Regarding data centers, so instead of transferring or peak shaving the data center electricity demand or use, there is a new trend of
moving less frequently used backup files to slower, cheaper storage places when electricity is expensive or the grid is stressed.
However, major challenges remain around robustness of the models, accuracy, and scalability, and for sure data governance. Another important topic was about data privacy. So rather than transferring ownership of data, future systems are relying on delegated access, anonymization, and aggregation mechanism that preserve privacy while enabling large-scale intelligence. Discussion also explored how data centers and electricity demand could be managed through cross-regional load shifting and peak shaving strategies, as well as the transition from large general-purpose models towards more smaller and compact and domain-specific AI models that are trained based on real urban data or building data to support more flexible and responsive forecasting of building performance and comfort expectations and building system overall. So that's it, the wrap up of day 2. Very interesting advancement in AI and data centers, and the overall target of all that is to decarbonize the built environment. See you tomorrow. So we are early in the morning of day 3 of the Building Simulation Conference at Hong Kong University of Science and Technology, and still the first keynote did not start. Today we will have 3 or 4 keynote speakers, but one of the most important ones, or the most important one, will be on data center. Another one will be about AI use in building performance simulation. So I will report on those 2, and then I will conclude after the sessions. So let's start the day with the keynote speaker presentations.
This morning we have 5 distinguished speakers from international China.
Alfonso and Marco, good morning. You will be on my YouTube channel, so say hi to everyone. Marco. So, because I'm reporting on the AI, and your keynote will be the key of the YouTube video, because it's focused on AI application. So you are very much appreciated, and we will listen to what you're going to say with very high attention. Good luck.
Okay.
Bye-bye.
I mean, let's be stressed, but okay.
Yeah.
Good
luck. Bye-bye.
Alfonso Cavagioli from Italia, from Politecnico di Torino. So, buongiorno. Yeah. Professor Alfonso has many distinguished high influence papers in energy and the other international journals, and also is the main expert for IBA. And today he will give us introduction about the digital chips and AI journey. So, welcome.
Thank you. Thank you very much. So, first of all, I'm very happy to sit here. I want to thank the organizers for inviting me to take this keynote. And just I want to thank you, Professor Shangwei Wang, because some of the aspects discussed in his presentation are in the introduction of my presentation. So I will try to go faster during the first slides to focus on the main aspect of my presentation. You know, this morning I was thinking to an aspect that is I've been working on the application of AI for enhancing energy management buildings from more than 15 years. But still, we are failing in an effective deployment of AI-based technologies. So I will try to discuss in this presentation which are, in my experience, the barriers that we need to face, and maybe to propose some solutions in order to enhance the scalability and the usability of AI-driven energy management in grid interactive buildings. This is more true, especially in the context of energy flexibility that was mentioned by Professor Shangwei Wang, where I will try to demonstrate how the AI-based solutions are becoming more and more a necessity and not only an opportunity. From the EU side, the very recent directive on European energy performance of buildings is pushing a lot on the role of digital technologies and ICT as key drivers for reaching the decarbonization strategies. It was introduced an indicator, this is the Smart Readiness Indicator, that aims to assess how much a building can potentially be smart according to the digital technologies installed in that building, including AI-based solution. And this kind of indicator takes at the center three key functionalities. The first two have been widely explored in the last few years. I refer to the optimization during operation of buildings through both the season support system services or automated system optimization. The second one takes to try to take into account which is the role of the human, and so it promotes a human-centric approach in the next generation of energy management, including the indoor environmental quality that I suppose will be discussed later by Richard. And finally, the third key functionality that is, in my opinion, is the most important is exactly the opportunity that a building needs to be read now to be flexible in the energy demand according to signals from the grid. So I think that this is the aspect on which we need to focus our attention because a lot of work, in my opinion, should be ready to be done in the next years in order to promote a reliable opportunity to give an active role of buildings in the energy flexible market. So as you know, now the objective is not only to save energy or increase energy efficiency, but to work on the, of course, management of the use of energy over time by providing a series of different services to the grid, big sharing, big load shifting, any kind of participation to demand response initiatives. And I think that of course, the buildings have an important role in this opportunity. We have a lot of enablers, including the thermal mass, the HVAC control, any kind of electrical or thermal storage. And we need to take into account which are the constraints. So we need to, of course, change over time our energy demand, considering the indoor environmental quality constraints, any kind of operational limits. We are working on that, especially with the aim to understand, as was mentioned by Professor Shangwei Wang, which is the real flexibility that we can beat to the market, and to try to assess this kind of flexible energy in a way that is characterized by low uncertainty. So to this purpose, we are working, for example, a lot on thermal mass. And if you take a look to the power imbalance, what we have realized is that we need to study this kind of contribution to this flexibility asset, considering a time domain, a frequency domain, and a spectral density, with the aim to understand which is the portion of the frequency spectrum that can be managed by varying the thermal load of buildings. So, which is the thermal load fluctuation that really a building can absorb, okay, considering the constraints of the indoor environmental quality or of the indoor temperature, according to the building envelope features, and also according to the terminal units and the heat transfer mechanisms that is at the base of the indoor temperature control. And of course, the contribution of HVAC system, of course also any kind of pre-cooling or preheating strategy can activate the thermal mass. But also other kind of opportunity need to be catched, including opportunity of varying the frequency of fan or pump, or varying the set point temperature, supply water temperature, or supply air temperature. But any kind of this opportunity is characterized by a different time response. And we need to take into account these different dynamics and time characteristics. Of course, aim is to, of course, try to provide services to the grid, but considering the so-called rebound effect and the different dynamics and the opportunity to have an approach that from reactive becomes predictive. So what is important in my experience is that these kind of control actions results from framework that are based on some key features. First, predictivity. Secondly, adaptivity. And third, a multi-objective approach. So these are the features that a control system should have in order to really control the flexibility asset in a way that can provide flexibility to the grid. And another important aspect is, of course, that now we need to coordinate the operation of a number of our buildings. So we need also a supervisory level with an advanced control that can support the opportunity to have finally an aggregated energy demand that respond to the needs of the grid. So we are working with different architectures, coordinated, cooperative architecture, or hybrid architecture Again, Professor Shangwei-Wang showed that kind of architecture in order to control both at single building level and at cluster level with this kind of advanced control. Okay, I mentioned some of these controls, MPC, reinforcement learning, hybrid control, but what I will try to discuss is that we have also opportunity to simplify the deployment of advanced control policy by an extraction of rules from an advanced policy based on, for example, reinforcement learning based control, which is the role of the digital twin in this process. First of all, we need to train this kind of advanced model. And we need to have a safe environment in which we can test and validate the effect of this control in terms of providing flexibility to the grid. But we have also another need that we need to exploit through a digital twin. We need to assess which is the impact of flexibility in advance, ex ante, to this kind of platform. Indeed, one of the challenges that we have been discussing also in the framework of Annex 96 from the International Energy Agency is to understand how to estimate the demand without activation and with the activation of flexibility. So one of the challenges is how to search for a robust baseline. And secondly, how can I assess the effect of any kind of flexibility activation, taking low the uncertainty. And then, ex post, through a so-called measurement and verification process, I need to compare the actual response against the counterfactual baseline, and so to verify how much reliable was the forecasting effect that I predicted. This is an example of a digital twin that I want to show you just to underline the architecture which we are working on. It is a co-simulation architecture that makes use of FMI standards for a municipality, a real municipality. And what it was really interesting from my point of view is that we were able to gather a lot of information from existing databases, including energy performance certificates or any kind of cadastral maps. We were able to use this kind of simulation platform based on FMI standards to both optimize the operation of these buildings and to assess the potential flexibility that they can provide. Okay, so what we have stood till now is that we need of AI if we really want to exploit the flexibility from buildings. But we have some barriers that we need to face. I summarize some of them here, but I just want to skip to the most important, in my opinion. First, the complexity in integration. Secondly, we need data if we want to work with data-driven modeling. We need to be aware that currently we have higher initial costs if we want to use AI, and also some uncertainty on the long-term provision of the energy saving that you can obtain. We have interoperability issues, and still we have skepticism when we talk about AI. So how we can try to address some of these barriers? So what we are doing in my lab is to include in any kind of application, any kind of AI-based framework, three kind of features: portability and interoperability by making use of semantic metadata model, transferability by using transfer learning frameworks and interpretability, where we are trying to extract very simple if-then-else rules from advanced control policy. So, just a few words about each one. The portability is the ability of a software to be implemented from one platform to another platform. What we are trying to do is to verify which are the opportunities that we can catch with consistent semantic models in order to contextualize in a standardized way the data that we have. Of course, we need to face some problems when we want to build a semantic metadata model. We have a number of different ontologies, so we need a multi-ontological approach. And even if we use the same ontology, we have a certain degree of subjectivity when you want to describe a system. And then your metadata, semantic metadata model, needs to be maintained over the life cycle building. And to this purpose, what we're trying to do is to automatize or speed up the process of knowledge graph generation. And especially, what I want to here stress is the importance to consider in the knowledge graph also all the information related to the control system, which is in this kind of reasoning that I'm trying to do with you. It is important respect to the opportunity that we can take from the knowledge graph is the semi-automatic generation of building energy models. So what we are trying to do is to demonstrate that thanks to a knowledge graph, a robust knowledge graph, you can then build a good first draft of a digital twin. Okay? But the other question is, who is in charge of the metadata semantic model, not the energy model? So, we can catch some opportunities to accelerate the process of construction of knowledge graph. To this purpose, large language model and generative AI can support a lot the automatic generation of knowledge graph. We are working with a multi-ontological approach. Here I mentioned some of the ontologies that we are using, and we have experienced a very reliable construction, automatic construction of a knowledge graph or trees of knowledge graphs through prompting by using generative AI. What about the transferability? Here, the opportunity is not only to enhance the portability, but to have some process that can help to use the knowledge that was acquired from source building and to put it in a target building. So here, the main objectives are related to the improvement of model accuracy, to lower the data in order to deploy any kind of advanced control policy, and of course to enhance the scalability of advanced control. Okay, we have been working on different frameworks based on a transfer learning. What just here is important to underline that with this kind of algorithms, we can support the scalability of any kind of model that can predict disturbances. But also we can work directly on the opportunity to transfer control policies. Another opportunity is to use all the knowledge that it is already embedded in an existing building automation control system that make use of traditional control to initialize the process of training. Okay? For example, just all the actions that are the results of any kind of PID or RBC control can help a lot to initialize your advanced control agent in order to speed up the process of deployment. We did it in a real case study collaboration with ETH. This is a case, in my opinion, very interesting, which we had two offices, a source office and a target office, and we first trained a DRL controller in a simulation environment. Then this controller was implemented, and then the same controller was transferred to the target building with an online training, okay? And finally, what was very interesting is that we developed a digital twin to benchmark the performance of our control strategies against other kind of control strategies. So, another reason that's at the base of need to have a digital twin is to benchmark different kind of control strategies that can activate the flexibility. Okay, so the so-called scenario analysis. Okay, some results. What happens when you want to scale up and scale out? Okay, we are working to different kind of architecture with the aim to understand which is the architecture that is more easy to be deployed in real life. And also how we can really handle the high dimensionality of observation space and action space. So we are working with multi-agent architecture, and also with the aim to track an aggregated energy demand through this kind of multi-agent control system. Finally, the interpretability. Okay, we know that we need to increase the stakeholder trustness in adopting AI-based solution, and I think that we need to shift from a techno-centric approach to a human-centered analysis in order to have more actionable insight as a result of our analytics framework. We are working on the opportunity to extract rules from advanced control policy, that is based on deep reinforcement learning. And also we are working to make some future engineering of the variables at the base of that tree that can make possible also to transfer this kind of if-then-else use from one building to another building. And which are the practical results? We have very lightweight model. It is possible to transfer this kind of use. It's easier to implement this kind of use also at age level. And finally, what we are realizing is that the results very close to that you can obtain with a more advanced control policy. Just a few words about the generative AI. Thank you. I'm going to the conclusions. About the portability, what we are realizing, experiencing, is that the large language model can help a lot in developing very robust knowledge graphs, also making use of more than one ontology, covering all the domains. About the transferability, the generative AI, in my vision, in the next future, will support a lot the generation of realistic synthetic data profile. And also the definition of archetype of source model that can already trained, that can be used for different kind of target buildings. And interpretability. We can really exploit the large language model to understand which are the outputs, which is the reasoning at the base of any kind of complex models, or also to ask questions about the model decisions or the action that have been taken from an advanced control agent. Some final remarks. Flexibility, of course, can unlock economic value. We need to connect the flexibility with the revenue. But what we need to do first is to lower the initial cost of AI-based solutions that are, in my opinion, mandatory if we really want to manage the different flexibility assets and we want to decrease the uncertainty in predicting the flexibility or in assessing how much flexible energy we can bring to the market. Bridging building AI domain. Okay, I just want to conclude with two remarks. The physics, it's very important, okay? So we are going more and more in a direction in which the hybrid modeling becomes, in my opinion, the solution, the best solution. And the main obstacle is not the algorithm itself, but is the cost, the trust, and the integration. I really hope that with this discussion, I was able to at least enable some reflections about these opportunities that we need to achieve as soon as possible. Thank you very much.
It was a very successful conference and I had a lot of behind-the-scene conversation with different professors. It was difficult sometimes to film with everybody, but definitely I had very intensive and rich exchanges, especially with Chinese colleagues, and this will give me an opportunity to continue building the network and knowing more and more about Asia. Also, it was an opportunity to learn a lot about the Singapore scientists who are working in this field, and I hope maybe in the future I have the opportunity to visit Singapore and its universities. So we are coming to an end of the Building Performance Simulation Conference here in Hong Kong at Hong Kong University of Science and Technology, and I have some closing remarks to share with you that are very important. Actually, one of the most important discussions we had in this conference this year was the presence of AI and the prediction that building performance simulation or urban simulation tools will be replaced by AI. And AI agents will take over most probably. So software like EnergyPlus or Transys or EDA ICE or Modelica will be an invisible infrastructure embedded in existing AI like Claude or Daobao in China or any other Kimi software. So instead of using simulation tools, the simulation scripts will be directly embedded in AI agents. And this will be future practices. Professor Da, future practitioners will not be able to open any more software, and they will directly use the AI agent, and they will not build the model anymore in a classical software like Design Builder, for example. So this will be very interesting because AI agents will be directly asked to optimize building for comfort or for carbon emissions or for heat waves or for life cycle costing or any performance requirement you are looking for. So the AI agent will generate the model and orchestrate thousands of energy simulation, say in EnergyPlus runs. We already saw in one of the sessions how IDF files are generated today by Claude or ChatGPT. And the AI agents will run these simulations and start to focus on the results. The implication means that this will be profound and simulation will not be anymore the bottleneck in the process of decision support. What we will focus more on will be informed decision making,
And in this future, knowing how to operate software, I think, will be less and less valuable, and we will be more focused on the scripts behind these softwares and how to validate, calibrate, and challenge the results produced by the AI-driven workflows. So this is a very important point that will change the industry, and I hope you stay tuned to follow what's going to happen in the next years.